In this lesson, we're going to learn about composite and inverse functions. A composite function is the result when one function is input into another. So in the example that I have here, g of x is a function in itself, and it is going to be the input into f. We can write f of g of x like I have done on the right. We can also use the notation on the left, which says f of g of x, and that's how we read it, f of g of x. The same thing here, our parentheses are another way of saying of, f of g of x. So if you just remember, those open brackets and parentheses are another way to say of. You'll know how to read it properly. Now, the domain of a composite function are all the values that are in the domain of g whose outputs are valid inputs into f. This is important. So all values that are in the domain of g whose outputs are valid inputs into f. So we put a value in, I'm going to do this in gray. So we put a value into g that's allowed to go into g. And then only those values that go into g that provide outputs that are allowed to go into f. So these outputs that go into f are the only ones that are allowed. So sometimes we have to limit what it is that we're putting into the g function so that we get specific values out that are allowed to go in for f. It sounds a lot more difficult than it is. I always mess this up. I need to be using my mouse here. Okay, let's go to an example and I'll show you what I mean. Here we have a composition function. We want to evaluate f of g of 1. Then we want to evaluate g of f of 1, and then f of negative 2, and then g of negative 1. So I'm going to rewrite these so that I can have some room here. And, okay, so we're going to rewrite this. So we have f of g of 1. I'm going to take 1 and I'm going to put it into the g function. So g of 1 is 4 times 1. So that gives me a 4 out. Then I'm going to take that 4 and I'm going to put it into the f function. So I put 4 into f and I get something like 29. Now, you might be going, where are you getting all these numbers from? Really what I wanted to do with this notation was just show you what's happening. 1 goes into g, you get an output, and then that output goes into f. I like writing this like this. So for me, it's a little bit easier to see when I do that. So g of 1, I'm going to figure out what g of 1 is. I'm going to do a little bit of work up above. So I'm going to go to the g function, g of 1. Well, that's 4 times 1, which is 4. So now I'm going to rewrite this. And this is no longer f of g of 1, this is f of 4, because g of 1 is the same thing as 4. Now I'm going to take 4 and I'm going to put it into the f function. So that's going to be 2 times 4 squared minus 3. 4 squared is 16. 2 times 16 minus 3. That's 32 minus 3, and that's where I was getting 29. So some of these problems require a little bit of work off to the side. So sometimes I'll go off to the side and I will just write my work out so that I can see it, make sure that I'm getting the right answer, especially since many of these do not require a calculator. You should be able to do all of these problems without a calculator. Okay, let's try the next one, g of f. So this time I have g of f of 1. Now is that going to be the same thing? Well, this time I'm going to do f of 1 first and then put that result into g. So let's see what f of 1 is. So f of 1 is going to go into g. So I'm going to come off to the side over here. I'm going to say, okay, what's f of 1? Well, f of 1 is going to go to the f function and put a 1 in place of x. So I have 2 times 1 squared, which is 2. 1 squared is 1. 1 times 2 is 2. Minus 3 is negative 1. So I'm going to rewrite this g of negative 1. Now I'm going to go over to the g function, and I'm going to put negative 1 in. So everywhere I see an x, I'm going to put negative 1 in its place, and I get negative 4. And you can see that f of g of 1 is very different than g of f of 1. Okay, let's try f of negative 2. So f of negative 2. Okay, the f function is 2x squared minus 3. I'm just going to write it over here. F of x equals 2x squared minus 3. And I'm going to come off to the side over here. F of negative 2 is 2 times negative 2 squared minus 3. So that's going to be 4 times 2 is 8. 8 minus 3 is 5. So that's f of 5. Now I'm going to try and find f of 5. So f of 5 is equal to 2 times 5 squared minus 3. 25 times 2 is 50. 50 minus 3 is 47. So you can put a function back into itself. So I'm just going to take this and I'm going to make it a little bit smaller in size. Don't know why it wants to grab that 47 there, so I might just have to shrink that too. Yeah, it's connected for some reason. That's okay. Now let's try g of negative 1. G of negative 1. Now, I really like to write my function within another function using the brackets and the parentheses. G of negative 1, well, g of x was equal to 4x. Let me double check that. G of x was indeed 4x. So I'm going to find g of negative 1. When I put a negative 1 in, I get 4 times negative 1, which is negative 4. So this is going to be g of negative 4. G of negative 4 is equal to 4 times negative 4, which is negative 16. G of negative 1 is negative 16. And that's how you find the numerical value of a composition of two functions. We're going to work with variables next. So now we're going to find a composite function and its domain. That means we're going to be putting variables in, such as x. And I still like to rewrite my function f of g of x. So I still like to write it with the brackets and the parentheses. You do whatever is most easy for you to see. You put an x into the g function, and that's what you get. I like to write it like this, where I have f of g of x is the same thing as f of, and then whatever g of x is. G of x is 2x plus 3. We're going to put a 2x plus 3 into the f function everywhere we see an x. Now, the domain, well, let's get to the domain in a moment. We know that in a linear function, the domain is all real numbers, and the range is all real numbers. And 2x plus 3 is a linear function. Let me use color right here, 2x plus 3. So that's a linear function. All real numbers goes in, all real numbers comes out. I'm also going to use a highlighter. G of x is 2x plus 3, just so that you can see that as well. 2x plus 3. And now we'll go back to just computing what f of 2x plus 3 is. So I go to the f function, and instead of x squared, I'm going to have 2x plus 3 quantity squared. And instead of 3 times x, I'm going to have 3 times 2x plus 3 minus 1. So instead of x squared, I had 2x plus 3. And instead of 3x, 3 times the quantity 2x plus 3. So 2x plus 3 times itself is 4x squared plus 12x plus 9. I encourage you to practice squaring binomials so that you can just do that multiplication in your head. Now I'm going to distribute the 3. So I have 6x plus 9 and then minus 1. I'm going to combine like terms, 4x squared plus 18x plus 17. 18 minus 1 is 17. That is f of g of x. I'm going to use my shape recognition pen to box my answer. It's cool stuff right there. Okay. Now, the domain of this function, the domain is all real numbers. This is a polynomial function. It's specifically a quadratic function, and all real numbers are allowed. Okay, let's try the other way. Let's find g of f of x. So g of f of x, I rewrite it, g of f of x. And f of x, I'm going to highlight in green. So this time I'm going to be putting the trinomial into the g function. So I'm going to be having an input of x squared plus 3x minus 1, and that is going to go into the g function. So instead of 2 times x plus 3, I'm going to have 2 times the quantity x squared plus 3x minus 1 plus 3. And that's 2x squared plus 6x minus 2 plus 3, which simplifies to be 2x squared plus 6x plus 1. And that's g of f of x. And again, I'm going to mess around with this shape recognition tool and box my answer once again. I have another quadratic as a result, and quadratic functions have a domain of all real numbers once again. All real numbers once again. Okay, let's do the composite function of rational functions. So a rational function has that variable in the denominator. So now we're going to find f of g of x. F of g of x. Now this is interesting because g of x has a domain where x cannot equal 1. Every number except for 1. And f of x has a domain of every number except -2. So all real numbers except -2. So we're just going to kind of write that off to the side because now we have some restrictions, and now we're ready to find f of g of x. So g of x is 4 over x minus 1. So f of 4 over x minus 1 is equal to, now I'm going to go to the f function, and instead of 1 over x plus 2, I'm going to have 1 over 4 over x minus 1 plus 2. This is called a complex fraction. That's a fraction within a fraction, and that we have to clear. So we're going to clear that fraction by multiplying each term in the fraction by x minus 1. I really don't like the way I just wrote that right there. It should be in the numerator. So I have 3 terms. I'm going to highlight them in yellow. 1, 2, 3. There's 3 terms within the fraction, the big fraction. I need to multiply each one of those terms by x minus 1 so that these x minus 1's clear and I no longer have a fraction within a fraction. So what that's going to leave me with in the numerator is 1 times x minus 1, which is x minus 1. And then in the denominator, I'm going to have, in the denominator, I'm going to have 4 plus 2 times the quantity x minus 1. And that's going to simplify to be x minus 1 in the numerator over 4 plus 2x minus 2. That's going to be 2x plus 2. I'm just going to factor just to make sure that nothing cancels out, and I don't have anything that cancels out. So my result, which is my answer, f of g of x, is equal to x minus 1 over 2x plus 2. Now, what can x not equal here? The domain of this function is x cannot equal -1, correct? Okay, so your domain is that x cannot equal -1, but there was another restriction in the original function. So in the original function, remember, you have to start with this domain first. So we start with this domain, x cannot equal +1. So that restriction is also in our final domain. Now when x is 1, you end up with an undefined value. Now, what cannot go into the f of x function? Well, what can't go into the f of x function is -2. So what do I put in 4 over x minus 1 for it to result in a -2? Well, let's solve this and find out. I'm going to cross multiply. -2 times x minus 1 is equal to 4. -2x plus 2 is equal to 4. X cannot equal -1. And there's your -1 right there. So that value came out naturally in our restrictions in our final answer. However, we still needed to go back to that original restriction from the domain, because this original restriction does not appear to have 1 for x equals 1. I can put a 1 in to this final answer here. I can put a 1 in, but I couldn't put a 1 in the very beginning, which resulted in my answer. So if I couldn't put the 1 in the very beginning, I can't put a 1 in at the end. It's completely restricted from the domain. So what's restricted from the domain? A 1 and a -1. What was the significance of this x cannot equal -2? That was for me to show you how 4x minus 1 cannot equal -2. And that restriction is -1. So the original restriction and then that output that gives us the restriction for the next one is also restricted. It's a little confusing. We really have to think about it. So let's write down what our restrictions are. It will help if you can write these down. Restrictions come from the initial restriction of g of x and the inputs of f of g of x, and restricted inputs. I'm going to put restricted inputs. So I'm going to highlight them. So our initial restriction was +1, and the restricted inputs of f of g of x was -1. And it just so happens that they both happen to be additive inverses. Sometimes it's not just a plus or minus 1. Sometimes they're two entirely different numbers. Okay, let's try a composite function where we're putting a function back into itself. So very similar with the rational function. So let's calculate f of f of x. Now I'm going to write my original restriction, x cannot equal -2. That's going to be restricted from the final domain. So f of x is equal to f of 1 over x plus 2. And that is equal to, instead of 1 over x plus 2, it's going to be 1 over x plus 2 plus 2. So everywhere we see an x, we put our new input of 1 over x plus 2. And then I'm going to multiply each term by x plus 2. So 1 times x plus 2, 1 over x plus 2 times x plus 2, and 2 times x plus 2. That's how we clear our complex fraction. So I have x plus 2 in the numerator over 1 plus 2 times the quantity x plus 2. So it's going to be x plus 2 in the numerator over 1 plus 2x plus 4, which is x plus 2 over 2x plus 5. My restricted domain, x cannot equal our original -2, and now it can't equal -5 over 2. We take that 2x plus 5, we set it equal to 0 or not equal to 0. 2x, it's positive 2x, equals -5x, equals -5. Divide both sides by 2. And we get x equals -5 over 2. So our answer, f of x is equal to x plus 2 over 2x plus 5, where x is not equal to -2 and not equal to -5/2. Now this might also be written in interval notation, -∞ to -5/2, -5/2 to -2, and -2 to infinity. So it could be written either way. Now, I love these types of problems. Find f and g such that the composition of f and g, f of g, is equal to h, where h of x is equal to 1 over x plus 1. Now, think about your parent functions. So our parent functions, remember some of them, y equals x, y equals the square root of x, y equals x squared. This is why it's so important to know these parent functions. Y equals x cubed, y equals, what was another one? 1 over x, and then I had a sixth one. I think I had a half circle. I don't quite remember because that was several lessons ago, but this is a good start. You can go back to that lesson if you did not study your parent functions. You want to know these parent functions off the top of your head. Really, you really need to make sure you know these. These are math facts. Just like multiplication is math facts from 3rd and 4th grade, and you use those moving forward. Same thing with your parent functions, your exponents. 1 squared through 25 squared, 1 cubed through 10 cubed. These are all math facts that you really should have at this level of your mathematical career. So if f is the parent function, right? So I have f of g of x. I need to put something into f in which its result is going to be 1 over x plus 1. So if my parent function, what could my parent function be? My parent function could be 1 over x. That could be my parent function. And then I would have the form, a fraction, a rational function, 1 over x. But I don't put an x in there. I have to take another fraction and replace x with x plus 1. So g of x, let's use a different color, g of x is x plus 1. So f of x is 1 over x, and g of x is x plus 1. F of g of x says you're going to take your x plus 1 and you're going to put it in for x, and voila, you get h of x, which is 1 over x plus 1. So that indeed is your answer. I'm going to rewrite it. F of x is 1 over x, g of x is x plus 1, and that is going to give us a composite function for f of g of x equaling h of x, 1 over x plus 1. It's cool stuff. Cool stuff. Let's have you try one. Okay, so let's see if you've got that. See if f is the parent function and g is the replacement function. So your parent function and then your replacement function. Which is which? Press pause so that we don't give it away. It's one of those crazy George Strait songs. We've got a parent function, and then we've got g is the replacement function. So what's staying? What is staying? The cubed function is staying. So this is a cubed function. So that's our parent function. And then what are we going to replace x with? Well, we're going to replace x. Do that in red. We're going to replace x with 1 plus x squared. So g of x is equal to 1 plus x squared, and f of x is equal to x cubed. Excellent. Hopefully you got that. Another fun problem that I like with these composite functions is the graphical representation. I really like the graphical representation. So what I do is I highlight. I make sure I know which graph is which. So this graph on the left is f of x, and the one on the right is g of x. And then you probably realize this from me by now, but I really like to rewrite these functions as f of g of 2. F of g of 2. Okay. But it's okay. If you want to put 2 into the g function, you can use this form right here and say I'm going to put 2 into the g function. And when I put a 2 in, I get a 2 out. So I'm going to take that 2 that I got out and I'm going to put that into the f function. So I'm going to come over to my graph on the left and I'm going to put that 2 into the f function, and when I put the 2 into the f function, I get a 0 out. Another way to look at this, if you rewrite it the way I did, is say what is g of 2? Well, g of 2, when you put a 2 in, you get a 2 out. So g of 2 is 2. And then what's f of 2? Well, f of 2, you put a 2 in and you get a 0 out. So that's A. We'll call that one A. Okay, let's do B. Let's go to the right and do B. Let's do g of f of 2. So g of f of 2. Well, what's f of 2? And I'm going to erase these marks right here. Well, f of 2, I'm going to go over to the f function, that's the one on the left, and when I put a 2 in, I get a 0 out. So that's a 0. So now we have to calculate g of 0. So we're going to go over to the g function on the right, we're going to put a 0 in, and when we put a 0 in, we get 4 out. Most excellent. Okay, you try C and D and see if you think you've got it. So make sure you press pause, give it a try, and then come back. Okay, for C, long story short, for C, f of g of 1, I got a 2. And for D, g of f of 3, I also got a 2. I also got a 2. So hopefully you got the same thing. Okay. I'm going to end this video here, and in the next video we're going to talk about inverse functions. So we're going to come back and we're going to talk about one-to-one functions and inverse functions to finish up this lesson.